And the next talk by Vladislav Barinov, Sterile Neutrino searches, dark matter, and cosmology. Please.
Okay, let's start. First, I would like to thank the organizing committee for the opportunity to be here today. And my talk is devoted to the sterile neutrino search, recent results in this field, and also dark matter and cosmology, of course. First, we know that our universe consists of dark matter, dark energy, and ordinary matter. In this slide, you can see general parameters of the lambda CDM model and the pretty picture for components of our universe. And of course, we cannot say about our universe without dark matter, because if we see on the CMB spectrum, we need dark matter component in the right panel. You can see how our universe looks like. This dark matter and without dark matter, the pictures differ significantly, and of course we need dark matter. And okay, what is dark matter and how was it generated? It's really complicated questions, and not only dark matter we can see in CMB spectrum, also for rotation curves and viral mass, for example, the coma cluster, or like first evidence of the dark matter, and for example, gravitational lensing. And now we have a lot of candidates for the role of dark matter particles, but in my talk I concentrate only on sterile neutrinos as light sterile neutrinos and sterile neutrinos, these masses of several kiloelectron volt. What's wrong is neutrino, and of course we know that neutrino has non-zero mass, and the neutrino oscillations, this is a strong evidence of incompleteness of standard model of the we have some of the anomaly results, for example, gallium anomaly, and for example, this reactor anomaly, but reactor anomaly almost resolved, but the gallium anomaly remains, the question remains open. And as for the light sterile neutrinos, we can see recently results of the best experiment, and in these experiments we got a very unexpected results, a very low level of registered electron neutrinos in the inner and the outer volumes in this gallium detector. And this is a very interesting, because results of the best experiment contradicts these results of the other experiments, for example, anti-neutrino reactor experiments and solar neutrino constraints from the Carl Junti recently papers. And it's a very interesting question about light sterile neutrinos. But I would like to say that light sterile neutrinos, these masses of several electron volts, it's not a good thing for the modern cosmology, because if we add these sterile neutrinos, light sterile neutrinos in our, for example, the CMB spectrum, we will see significant distortions from standard lambda CDM predictions without the light sterile neutrinos. It's not good for modern cosmology. And what is it? What is the best result? What is the gallium anomaly? It's maybe a Lucas-Ray effect or something like statistical fluctuations. We don't know. But actually, the question remains open. And further, I concentrate only kiloelectron volt sterile neutrinos. And these neutrinos, it's more interesting candidates for the role of the dark matter particles. And if we have a sterile neutrinos, this mass of several kiloelectron volts, these sterile neutrinos it's not heavy dark matter, but the range of the speed, the velocity of these particles in the galaxies, for example, enough to these particles can construct dark matter, and we can constrain parameters of these sterile neutrinos using X-ray observations, for example, from for our galaxy and other galaxies, and because these particles can decay into one active neutrino and a photon, and because we have a simple decay, one particle to two particles, the spectrum is monochromatic, and the energy of X-ray photons of these decays is the mass of the energy of X-ray photons equal mass of sterile neutrino divided to 2. And okay, these searches of light of these kiloelectron volt sterile neutrinos was the searches was driven for the recently results from 2014 year in 2 articles when the people found some interesting results in Persei galaxy cluster and M31 galaxy, Andromeda galaxy, and they found evidence of sterile neutrino, these masses of 3.5 kiloelectron volts, and it was a perfect driver for the further research in this direction. And I can say that further research didn't find the evidence of the presence of this line, and now we have very strong constraints on the parameters of sterile neutrino in this energy range. And okay, how can we constrain the parameters of these sterile neutrinos? We can calculate the intensity from the signal flux. And we can calculate dark matter column density on the line of sight if we, for example, if we here, this is the sun position, and if we look at the center of our galaxy, we can calculate dark matter flux from the cone. This angular radius, and calculate signal flux. And if we know the level of the background, we can compare, for example, signal to noise ratio, and we can compare our predictions in case if we know any signal, and if we know the level of background, we can constrain the parameter space of this sterile neutrinos. I mean parameter space, I mean mixing angle, of course. Okay, but if we want to calculate the fraction of dark matter in our galaxy and constrain parameters of sterile neutrinos, we should use some dark matter profiles in our work, and mostly the people use Navarre and White profile, these various parameters. But I should mention that uncertainties in dark matter profiles, even for our galaxy, has a significant uncertainties. For example, in the left panel you can see dark matter density profile in our galaxy, in the Milky Way. These various dark matter profiles, and the scattering reach a factor by 2 in these estimations. And in the right panel, you can see column density of the dark matter. Column density, this is the integral from the dark matter density in the line of sight and in a given solid angle. The significance is very big, the factor by 2, we can try to constrain parameters of sterile neutrino using some of these profiles, and for example, if we know the sum of these profiles, and if we know the ground level, we can get constraints. And further, I will show you that uncertainties in this profile, it's not significant if we mean the statistical fluctuation in, for example, in the ground spectrum, if we use blunt sky observations. And okay, as for X-ray instruments for these searches, we use data and preliminary estimations for the E-ray-zeta and the Arctic Sea X-ray telescopes, and also we use data for the NuSTAR telescope. And first, I would like to show you our expectations about the constraints on parameters on sterile neutrinos. And in the left panel, you can see our expectations. The red line, this is the expectations of constraints on parameter of sterile neutrinos for the E-ray-zeta telescope for the 4 years of full sky observations. And the blue line, this is solid blue line, this is the same thing, but for the Arctic Sea telescope. The purple line and the orange line, this is constraints for the E-ray-zeta and Arctic Sea telescopes, but not for the direct astrophysical observation of the in the cone around the Milky Way, this is constraints from the correlation analysis of the cosmic structures, and these constraints is much more weaker than the direct constraints from astrophysical observations. But of course, if we see in our universe in general, we have a fraction of ordinary matter and dark matter, like 1 to ratio 1 to 5. But if we see in some big galaxies, we see that dark matter and ordinary matter, it's the ratio of dark matter and ordinary matter is much more big. In the right panel, you can see recently constraints obtained for the E-ray-zeta telescope for the EFITS data catalog, and possible constraints for the more statistics in the red and blue regions. And we can see that our expectations, for example, as for E-ray-zeta, our expectations only consist of these data obtained by other independent group using the EFITS data, if we recalculate for the given time of exposure, of course. And also we got constraints on the parameters of sterile neutrinos using the 2 years data of full sky observations for the Arctic Sea telescope. In the red line, this is our constraints for the Arctic Sea, constraints on parameters of sterile neutrino for the Arctic Sea telescope, and blue dashed line, this is our expectations without statistical fluctuations. And we can see in the level of the statistical fluctuations, our constraints consistent with these real data constraints. And as for the new results, I would like to present our constraints on parameters of sterile neutrinos using the NuSTAR 11 years data, and we use a lot of observation positions, and we use combined analysis for the both models, like model A for the NuSTAR telescope and model B for the NuSTAR telescope, and we construct, we got combined spectrum of blank sky observations, and we obtained the very strong limits on parameters of sterile neutrinos. And a few words about our details of our analysis. We use a very simple model. This is a solar component power law, and CXB component. This is a driver model, and we fit our spectrum without dark matter. And after that, when we got a number of our parameters, we add the dark matter line, like a Gauss line, in our model, and we set the upper limits of the amplitude of dark matter in the spectrum, and if we recalculate amplitude to the mixing angle, we can get the constraints on parameters of sterile neutrinos. And in this plot, you can see a spectrum from NuSTAR blank sky observation, stacked spectra. Of course, now this is spectrum and our fit without the dark matter line, and this is the ratio, the model ratio. You can see the fluctuations in this spectrum, but the fluctuation it's not big because we have enough statistics, and in this plot we didn't use systematic corrections, and if we add some systematic corrections for our model, we obtain a very good result, and his squared statistic becomes much better. And of course, using this spectrum, stacked spectrum from the blank sky observations, we got constraints, new constraints on parameters of sterile neutrinos. In the left panel, you can see our constraints on square of mixing angle, and a lot of colors line. This is constraints for the various dark matter profiles, and black line and the green and yellow regions. This is 1 sigma and 2 sigma percentiles for our median constraints. If we use not only the one original stacked spectrum, but we simulate 1,000 fake spectra, and test our constraints for the robustness of the various statistical realizations. And you can see, for example, very weak constraints in this region, or for example, very strong constraints in this region. You can see that these fluctuations almost inside the 2 or 2.5 sigma region. Actually, we see no evidence of the presence of the line of sterile neutrino line, like for example, in 3.5 kiloelectron volts and so on. In the right panel, you can see our constraints for the decay rate. This is the same picture like in the left panel, but for the decay rate, for more convenient the other results of the other groups, and comparison results for the other groups. And okay, this is our final picture. the gray line, the gray regions, this is the previous NuSTAR constraints, and hatched region, this is the XMM Newton constraints, and the NuSTAR 20-year constraints. And the red line, this is our new constraints from the NuSTAR data collected for the 11 years of observations. And we can see that in this region of the mass of sterile neutrinos, our constraints are very, very close to the VDN and MSM limits, and the window for the kilo electron volts sterile neutrinos is very, very small. And I think in the near future it's maybe possible to close this window and to provide very strong limits. And in this region of mass ruled out the allowed region of the parameters of sterile neutrinos. And for example, for the comparison of the previous NuSTAR constraints, you can see these previous constraints. This is the blue line, this is a gray region. In this picture, this is a blue line, and you can see 3.5 kilo electron volts anomaly, and this result is closed. And in the right panel, this is the same picture, but in the zoom, this is a line and constraints. And I think this is a really good results, because we can exclude a lot of we can exclude parameters of sterile neutrino in the very big range of the energy and masses and mixing angle. It's strongest constraints on parameters of sterile neutrinos in this energy range. And I would like, in the end, I would like to say a few words about cosmology using the X-ray telescopes, and we can use X-ray data not only for some constraints on the parameters of sterile neutrinos or some exotic processes in the universe, but I would like to mention, I would like to say about the recent results of the E-Rosetta constraints on the cosmological parameters using galaxy clusters. And this is the results from the constraints of sigma 8 and omega meta parameters from the first full sky survey. This is a very interesting result, because we have small tension between Planck data. The Planck results, Planck constraints is something here, but we cannot see it because the contrast of the slide it's not enough for the picture. Yeah. You can see only right panel. Yeah. It's a very interesting result. It's a very complicated analysis, and we can use galaxy cluster for the cosmology. As several years ago, people say that we cannot use galaxy cluster for precise cosmology because uncertainties is very big. Yes, and the uncertainties is very big, and we don't know systematics effects exactly. But now we can do it, and I think in the future it will be very strong probe for some cosmological studies. In the end, I would like to highlight some interesting results, interesting challenges in the modern cosmology. For example, such a mission like SRG, Athena, and Lynx in the future to provide us some very interesting results in cosmology, search in the candidates for the role of dark matter particles, and so on. I think we will see a very stunning results in the cosmology in the near future. Thank you very much for your attention.
Thank you. Questions?
Well, thank you, Doc. If I get correctly, you said that you're interested in the neutrino starting from the mass of 3 kilovolts, but in the final picture, the lower mass is 6 kilovolts. So, if I get it correctly, how does look constraints on the left-over part?
You mean lower mass than 6 kiloelectron volts? In the lower mass range, I can show you this picture for the E-zeta constraints. If you want mass lower than 6 kiloelectron volts, but for the hour constraints, we did not constrain the mass of the smaller than 6 kiloelectron volts because we use NuSTAR data and RTC data mostly, and the sensitivity of these X-ray telescope, it's more the best level of sensitivity starts from 6 kiloelectron volts. Yes, but of course for the E-zeta it's possible, and but because we want to show constraints as for E-zeta and as for RTC and as for NuSTAR, and compare the results in the same energy region, and we chose this energy region just for because the best sensitivity of these X-ray telescopes.
Thank you for the talk. So I have a sort of technical question. What is the target for observation with this, say, NuSTAR? Is it a diffuse signal or is it a Milky Way center? Because lately it seems that observing the Milky Way center is the most beneficial strategy.
Thank you for this question.
Yes. And one another small question. In this NuSTAR constraints, one of your last slides, is the older constraints in some region is stronger than the newer constraints. What is the reason for this?
Okay. The first question, the answer, we use blank sky observations of the Milky Way because we see in the various places around the sky, and you can see these observations. The size of the one observation is near 4 square degrees, and when we combine these observations, we provide a stack analysis of this observation, and we exclude the galactic ridge in the minus to plus 3 degrees around the galactic ridge. We exclude this region because some astrophysical origins, some signals, systematic. It's very difficult to analyze what's happened in the center of our galaxies, and we exclude this region. Yeah. But as for the observation, this is a blank sky observations. These are the sources. We remove like point-like sources and extended sources, just only blank sky. And as for the second question, can you repeat, please?
Yeah, some older constraints of NuSTAR is stronger than your actual constraints. What is the reason for this?
Okay. This is the reason is statistical fluctuations. And if we see on this constraint, this is our new constraints. And if you see the older NuSTAR constraints in this energy region, you can see that In previous constraints, NuSTAR used the 20 megaseconds exposure. But in this region, in these constraints, we use 200 megasecond exposure. And the constraints, the behavior of the constraints like the root square of the ratio of exposure. And 200 divided to 20 megasecond, and the root square, it's a factor by 3. And our constraints in the mean are better than previous constraints at the factor by 3. Yeah. But this is a statistical fluctuations. It's yeah. And in this plot, for example, blue line, this is just one realization of the spectrum from the sky. But statistics, it's
May I ask you to show again your final plot with hatched regions? This one. So I see that you have the worst constraint exactly at 7 keV. And if I understand correctly, your red line does not exclude the 3.5 keV. So it is exactly by chance at the same energy and at the same angle, yes?
Yeah, thank you for this question. This is a very interesting question, because if we see in this region, yeah, you're right, because this is a very big constraints in the parameters of sterile neutrinos. But if we see in our spectrum, you can see this point. This is a sterile neutrino line. Just it's a joke. But this is the one point outside the mean ratio, and this is just a statistical fluctuation. For example, you can see this point here and here, and if we compare our results, our data with our model, the big constraints due to the fact that our data lies much higher than our model. And if we generate some fake spectra to study statistical fluctuations, you can see that this deviation almost inside 2 sigma region. And if it possible signal flux, we know strong evidence, because the significant level of significance of this signal just 2 sigma. It's not a strong evidence. It's not a 3 sigma or 4 sigma. It's not a strong evidence of the line. This is just statistical fluctuations. But as for 3.5 keV, this is this line and 7.
Right.
A little bit, yeah.
Right.
Yeah.
Yeah, but you can show there was a plot with other limits, for example. Yeah, that's one.
Mm-hmm. Yeah. Example. 3.5
Special
keV.
study, and also there is an XMM results and the results of the
Yeah.
NuSTAR previously.
Yeah.
Could you show once again the limit from NuSTAR? You have two lines for BBN1 and BBN2, and what's the reason for the big difference between them? And
on Monday was a perfect talk by Dmitry Barinov about the sterile neutrino constraints, for example, theoretical limits, and the difference. Well, there are 2 codes for the calculation of dark matter line, like sterile dark matter code and another code, and this is a strongly model-dependent calculations. and now we don't know what's
Is
right
there,
answer.
are there any significant differences between the models behind the code?
Yes, because we have two codes, and both codes give us different results.
Yeah, but the codes represent some theoretical model. Is the model different or
Yeah,
not?
theoretical model and some calculations technique. Actually, as for me, I didn't use this code. I used just only results of this code. And now in the literature, we know that there's differences between the answers from the various codes.
It's not completely understandable because
Yeah,
is it possible to write another code to give a
of course,
line
yeah,
toward
yeah,
the support?
it's possible, but it's very.
No, but will it give a result beyond below toward the spaghetti below? Is it possible?
You can obtain another result. Yeah. With a new code, surely.
Okay.
Yeah, but it's very.
I'm quite sure. You know,
Yeah.
You will be able to reproduce.
Okay. More questions? Questions on the other side?
Thank you for your talk. My question is about the possible radiative decay of the neutrino. So you showed that. So just to get an idea about the time scale. So what could be the lifetime with respect to the decay, taking into account the allowed parameter spaces? And the other question related to this channel also that if we reverse the process, so we can get a process in which the neutrino interacts with the photon, and in the final state we get a sterile neutrino, and could it affect on the cooling process of some astrophysical objects, or it is too small?
Thank you. As for the lifetime is much more bigger than the age of our universe, because in other case we cannot construct dark matter in halo of the galaxies, and for example, the galaxy cluster. The lifetime of the dark matter particles should be equals or much more bigger than the age of the universe. And as for the second question, actually I don't know. I should think about this. Actually, we can discuss it later maybe.
Yeah, there are limits from supernova. Yes, there are some limits depending on the mixed angle from supernova.
Okay.
Okay, let's make the speaker again.